Alright, so today, we'll make sure it's recording good. Today I'm going to talk about undecidability and halting problem. This is actually a very theoretical presentation, so you're going to have to sit back and kind of just work with me on the theoretical side, but it has an incredibly important application. And really the question we're trying to answer is, why is software testing done the way it is? Why don't we just have a program that can generate the test cases for us, and then we basically just validate that the test cases make sense, and then we move it on from there? Why can't the test cases be automated? Why do we have to do it by hand? Because trust me, if someone could do this testing, automate this testing, it'd be done. So let's go ahead, and this has to do with the halting problem. All right. You have to understand decision problems. They can be captured in languages. I know we're going to theory. But the problem determining whether a number is divisible by 7 corresponds to the language of all strings that form numbers divisible by 7. So finite automaton, aka a Turing machine, for division by 7 solves the problem and represents the language. All right, what this is saying is we're going to call it a language. Capture as languages. We can use a Turing machine. A Turing machine is a theoretical representation of how powerful our computers can be. In actuality, it's more powerful than what our computers, modern computers have, and actually anything in the foreseeable future, unless of course quantum computing comes out, then we might have something a little more powerful. All right. You don't recall how to do problems with Turing machines? I get it. Turing machine is going to run the input strings and the language, and if it's when not acceptable, we don't care, because the Turing machine is going to halt. And otherwise it's going to leave yes when it's acceptable, no if not. So you have 3 states of this machine is the big thing. You can either say yes, this was correct, no, can't be no, this is incorrect, in which case that means that the machine made a decision because it decided yes or no. But your third state is Turing machine just halts and doesn't print something out, aka something bad happened. Undecidability problems. All right, this is where it gets a little confusing. A decision problem or language is decidable if there's a Turing machine that solves the problem. AKA, if you have a problem, there exists some program out there, some Turing machine, that will say yes or no to the problem. Now keep in mind, all we care about is that it says yes or no. We're not having it spit out a long piece of information. We just want to say yes or no. A problem is undecidable if there is no Turing machine that solves or decides that problem. So it's undecidable if that program does not exist. Now notice this is actually going to be hard to prove because you actually prove that it's impossible for the program to exist. Keep in mind that solvable, unsolvable are sometimes used instead of decidable and undecidable. So you can just think of solvable and unsolvable if that helps. Here's the halting problem. Given a Turing machine P and input I, does P halt on I? Okay, can we create a Turing machine where you give it 2 inputs, a program, and an input to that program, and the Turing machine just tells you whether it halts or not? Does that program actually exist? Well, unfortunately, it's undecidable. That is, there is no program Turing machine that can solve the halting problem. In other words, we can't even write a program that tells you if something halts or not. Now hold on a second. Why is this so important? Well, if we can't find out if a program halts or not, what hope do we have that we can write a program to generate the test cases? Because we don't know if the program halts or not. How can we even know that we've generated enough test cases, or even generate a partial list of the test cases? Or what portion of the test cases we have? We can't tell if the program is going to halt or not. That's what this is coming down to. And since no one can write this program, we're effectively going to have to do testing the way we are. But let me go ahead and at least try and explain to you why this program or halting problem exists and why it can't be solved, because that should give you at least some insight into why we have to do it as opposed to a computer. Well, here's the problem. So how are we going to prove it? Well, we're going to first assume the program exists and then essentially say that it's a contradiction. We're going to assume the program exists and then show you how we can construct a situation where it just can't happen. So it's proof by contradiction. Hopefully you all remember that. But we're going to have, there's such a program, its inputs would have 2 portions, the program and the input to the program being fed to it. Its output would be yes or no depending on whether P halts on input I. So we're going to suppose it's decidable and arrive at contradiction. If it's decidable, then we know that giving P and I into a Turing machine A, it's going to give you yes or no. All right, so we're going to assume that this does exist and show you why it can't. So we're going to create a program B. Now this is very common. We say program A exists. We're going to create a program B that has a couple characteristics of program A. Now it's going to take its input of program P. That's all its inputs, just take program P. In B, P is duplicated so that there are now two portions on the input tape. And then this new input's fed into A. So in other words, A is going to be fed program P as a program, and the input is also going to be the program P. Hopefully you're still with me. When it is about to print no, print yes instead. And when it's about to print yes, send the program into an infinite loop. All right, that's going to be weird. Just stick with me. All right, here's more pictorial of what's going on. Here's program B with program A inside of it. Again, I think this is going to help a lot. It takes input P, it's going to make a copy of it so that A takes the program twice. So remember that A needed two inputs, now we're just copying and putting it in there. When A produces a yes, we're just going to go into an infinite loop. And when A produces a no, we're going to say yes. That's it. That's what this program does. Program B takes a program P as input, prints a yes if program P does not halt. So if P does not halt, it's going to present yes. Because notice that after you put it in there, it does not halt? No, let's say yes. But it goes into an infinite loop if P does halt. All right? Just stick with me. I know it's a little weird. So there's two possibilities. It prints yes. Well, that means that B halts on input B. But if B does not halt on input B, it's a contradiction. Well, okay, well, what's going on here? Well, if it's saying yes, then that means that P, when put into here, does not halt. But we're saying it does. Oh, hold on a second. I did that wrong. B halts on input B, right? So that's when it would print no. But if B does not halt on input B, now it's a contradiction. Okay, what's going on here? We're taking B and feeding it back to ourselves. I know this feels like Inception, but now we're going to take this program right here, and we're going to feed it into itself. All right, so we've been feeding ourselves a bunch of stuff. But that's the point here, because this is a program. It's B. We constructed it, and we can put B into itself. So what's going to happen? We put B in here, P and P, and then A is going to say it doesn't halt, and then input a yes, which means it's going to come out with something. But we just ran program B. How could it halt? Because we just determined here that it would not halt, yet it pushed out a yes. So that's a contradiction. Or it goes in an infinite loop. Okay. So that means that it goes into an infinite loop, aka B does not halt, but if we put it into here and we fed it to A, it just said that it did halt. That's also a contradiction. So this program, hopefully you can see, going yes, infinite loop. Hopefully you can see if one, while one, you can do an infinite loop. Hopefully we can all do infinite loops. No going to yes, hopefully we can all see that program is pretty easy to write. Making a copy, hopefully we can all see that's pretty easy. So obviously this is correct, that's correct. So for B not to be correct, the only thing left is for A not to be correct. And there's your contradiction, and why the halting problem cannot happen. Notice we're feeding B into itself. Hopefully that makes some sense what I was talking about here. So what is this? Let me step back and let you look at this, because I know this can be tricky at once. You're feeding B, make a copy into B, but if A says that B does halt, then it goes into yes, it halts, but now we're in an infinite loop. Whoa! But it did halt. That's a contradiction. Otherwise, we're saying it does not halt, but we just said it did. Also, how are we actually going through it? So there's either thing forms a contradiction, which means B cannot be correct. And if B is not correct, that means some part of B, at least one part of B, cannot be correct. Making a copy is correct. We can write that program. if yes, infinite loop, we can write that program. Inverting no to yes, we can write that program, which means A is the only thing left that has to be incorrect. And here's your contradiction. Consequences. We cannot write a program to perfectly test if a program of significant size completes. Sad face. That's a sad face, just so you know. It also follows eventually we cannot write a program to prove another program of significant size is correct. All right, I'm saying significant size here because by sheer technicality, a two or three state Turing machine can be solved for these problems, but no app or anything out there is a simple 2 or 3 state Turing machine. Anything of any importance is going to have plenty of states and will need a full-on analysis. So what have you chosen to do instead? Well, we've really just left down to testing. There's just not much else we can do. We just have to sit down and test it. Hopefully this also gives you an idea of why testing is done the way it is and why certain tools exist to aid, but it doesn't give us a lot of power that some people might expect it to give us. Now, lastly, if my presentation was confusing, I think this video actually does a very good job of explaining the halting machine or halting problem. Please go ahead and jump on and review it if necessary. And that's it for today.